Hi there, this is Olivier coming at you from jolly old London, and today I wanted to talk a bit about algorithms, and in particular a shift I've just made in the way I do them. For those who don't know, studying algorithms is an important part of being a software developer. I think even if you're just doing some light JavaScript, it's not something you touch very much. Learning your algorithms is important. Things like how to make your own arrays, things like well, things get more complicated from there up. What I'm using as an example today is a binary search tree, which I was revising this morning. And one thing I've always done the long way round is testing these algorithms. Now, a lot of people, when they write them out, do them on the whiteboard, and this is traditionally how I do it. You can see just in the background here, I've got a little whiteboard thing set up with the tasks I've got to do today. And doing it on the whiteboard is great because you can sort of map things out and it makes you very flexible, and it's often what recruiters and what interviewers will ask you to do in an interview. However, even if you T-diagram, which is a way of testing your code on the whiteboard, you still don't really know if it's going to run the way you're expecting. So the best thing to do is always to actually type it up and to run your code. So here we have a typed up function or other class, and it's for a binary search tree. And for those who don't know, a binary search tree is it's a data structure, just like an array, except that this one is cool for a lot of reasons. And that's really beyond the scope of this video. If you want to know more about binary search trees, I encourage you to Google. I think that HackerRank has some really good videos in general. The point is, I've written this out, and I now want to know if it works. And one way you might think of doing this is, well, I'll just write some code here at the end. So I'll say, okay, let's write some variables. Let's say let my BST, and I'm going to say this is going to be equal to a new BST. And we continue typing away like this, and so then I'd try adding nodes. So I'd say my bst.root equals my bst.node and put in a value there or something. And I could write this out. And again, it's not important that you know what a binary search tree is or what exactly this code here is going to be doing. What's important is that you recognize that this is pretty brittle. Like, I'm going to code one example here, right? And I'm going to run it. And then I'm going to see if I get any errors. And if it does, I'm going to have to go back and I'm going to have to debug, and I'm going to have to work out in what's going to end up being quite a few lines of code, what went wrong. And that's not really very efficient. And what you're sort of dancing around here is a notion called REPL, R-E-P-L. And so if we bring up the definition I've got here, boop, regard the definition. It's called a read, evaluate, print loop. If you're using REPL, then you're in a situation where you can write your code. It's not just going to be thrown away as soon as you close your session or whatever you're doing. So a lot of people are used to, for example, coding in the browser, and if you click here, so I'm in Safari, most people are in Chrome, but I'm in Safari. If you click on the console here, you can just type some JavaScript. I can say 1 + 1, and it'll tell me that it equals 2. I can say variable my face equals in a box over there, and then I can call my face, and it says in a box over there. So what I'm doing here is I'm typing stuff in, the console is reading it, evaluating it, printing it, and this goes around in a little loop. And it's very, very useful, this is, because it allows me to quickly get a sense of how my code's running and what kind of things I want to do. And so when you're writing more complex algorithms and you want to do this, you don't really want to just have to type out long form, for example, all of this into the console and then hit go, because obviously going back and editing it or making changes becomes very time consuming and is just generally a nightmare. So instead, you want to write it in a file like you would most of your programs. I'm sorry I'm switching from sides like this. This is my first time recording a video and I'm It's mirrored. Like that is where my function is. Where was I? Yeah. So you don't want to be typing this just out in the console. You want to save this in a file, and then you want to play about with it. And this presents a challenge. So just to be clear, what we wanted to do in the very first instance was take a step up from just writing stuff on a whiteboard. In the second instance, we've got two options. We can either write out our code long form here, or we can write it out in the console. And neither of those really work for large complex algorithms, because what you want to be able to do is you want to write some code and then you want to play with it. And you want there to be a permanent version that you can go back and work on. So it does look like Node is actually slowly coming up with a REPL module. It's in Node version 9, so it'll slowly trickle through. But for people who are in the land of Node 4.7 or Node 6, that's not really an option. And I wanted to find a solution that worked with today's technology, and it turns out there is one. It's the .load command. And Node is like I've been talking about it a lot, but all you need to know about Node is that it allows you to run JavaScript everywhere. So you want to test out your algorithm, you can install Node on your computer. There's, again, lots of guides on how to do that. I'm not going to go into it. And this is my terminal. Looks a little different to most because I've taken some time to make it look pretty, but let's start the Node environment. So here I am. Now if I type in JavaScripty things, it's going to do JavaScripty things. What I want to do now is bring this code here into my Node environment. So what you do is you would type .load. And now I'm in the right directory. I made sure I'd navigated to the right directory already. Again, if you don't know how to navigate directories in the shell, then Google it. It's not hard. So I type .load, I type class bst.js, which is the name of the file. And hey, let's now run through the file. And as it ran through it, it handily printed it out for me. So this is really cool. And let me show you why. So let's create a new variable here. I'm going to create a new tree. So BST for binary search tree equals a new BST. And again, you don't have to know what this code is doing. It's just important to see that what I'm doing now is just choosing whatever I want to type using this code and getting to test it out. So if I type in now BST, it'll tell you that it's a binary search tree and it's got nothing in it, which is what we expect at this stage. But I can say bst.add and use my add function I wrote, or whatever function, whatever it is you're doing, and I can add a new node. So let's say I start with 20. And here I've found my first error, which I'm now going to bug fix. Okay, yeah, I see what I've done. So here we go. What I've done here is I said that if the tree was empty, we should be appending the node to it, and turns out I renamed it new node. So let's pop back into the file and rename this new node. Save that, bring me back up again. So let's hop out here, reload node, and let's load up my file. So if I load up, let's create a new BST. Well, that would be because I typoed. Const BST equals new BST. And so BST is the name I gave my class here. You can see it came through here. So I'm creating a new one. Yeah, we have a new one. Now let's add some nodes to it. bst.add, I'm going to add 20 as the first one. So a binary search tree, the idea is that it structures data as you add it to it, and it's very, very fast at getting data out of it. So what I just want to do here is add a bunch of values and check that everything is doing the thing that it's supposed to be doing. Okay, so now I've added all these values, and that's great. I've been able to, I can see that I haven't any errors adding them, but now I want to see what does my binary search tree actually look like. And so this is another problem you get when you're trying to test these kinds of things. And if I was just doing it in this file, I might write all this code and write all these add statements, and then how do I know that my tree is actually in the right shape? Well, the nice thing about doing it in the console, the nice thing about doing it with the REPL loop, is that I can just type in BST here, and it's going to print out some stuff about the binary search tree. Now, it won't show the whole tree. It only goes a couple of levels deep. And I might want it to go a bit further, so if I access the root, it's going to show me a little bit more. So while this might not look particularly useful at first glance, it is incredibly useful, because what I can now do is I can actually map out my binary search tree. So let me just pop this note up. So I'm actually working, scribbling on this note on my iPad, so that's how this is syncing through. So if we look here at the code, I can see I've wanted it to print the root, and so it says the root has a value of 20. Great, well I'm going to stick in a value of 20. Hooray! So what I'm going to do is I'm going to just draw in the left, and I'm going to draw in the right, and I'm not going to wait for the iPad to catch up. I'm just going to do this, and in the next video, hopefully, it'll be faster. So let's go off. We'll say we've got one on the left, and that is going to be a 4. We've got one on the right, and that is going to be a 50. Excuse my excellent handwriting as it appears here. And then I can see that on the left node, it has a left value of -20 and a right value of 12. So let's go one down here. So that's -20. And it's got a right value of 12. And then the 50 has a left value of 27. And it's got a right value of 1000. Super. And what you can see here actually is, ooh, look at this, there's still an object in here. Now that means it's going another level deep, and it hasn't rendered it. So I can see here, I can see it in a number of ways. So 12, I know that 12 is there. And so I can work out that's gone left and that's gone right. Or I can just trace this through and I can say, okay, so we've gone left and we've gone right. So now what I want to see is bst.root.left.right. And I can see that coming off 12, we've got nothing on the left, and then on the right, we've got 13. So let's put on the right there, we've got 13. Okay, and maybe I want to do one more test, because one thing about binary search trees is what happens if you add a value that's already in there. So I'm going to add 13 again, and I'm going to add 12 again, and we're going to see what happens. bst.add, let's add 13, and bst.add, and let's add 12. Okay, now let's go back and have a look at that same node as earlier. Okay, so this is interesting now. So you can see that 12 has a right child value of 12. Now that's not right. This is very useful. I can see that something's gone wrong. Actually, no, I just made a mistake in the way I was annotating it. That's embarrassing. So we already had a duplicate there. You can see that 12 had on its right 12 and it had 13. So let's do that. We can put in a 13. And coming off, so we've got 12, 12, 13, and then it's got a left and a right. So what I want to do is I want to go left, right, right, right. Okay, and we can see that it's now got a left value of 12 and of 13. And just take a moment to think about what this actually means in terms of being able to work with algorithms. What I'm able to do here is write up my code, play with it, and then visualize the output. And I know it's taken me a long time to explain it all, but when I did this without talking it through for video, this took me about, I don't know, a minute to write up the code once I had my algorithm on my whiteboard, and it took me about a minute to punch in all the values. And then I can map it out. And now by looking at this tree here, I can see, well, is my algorithm working? And a cursory glance would say that it is. So that's exciting. And now I can do more interesting functions. I can write a function to balance it. I can write a function to calculate the depth, and I can test them. And I can do this in a very intuitive and interactive way, which isn't really possible if you're trying to just work in the console. It's not really possible if you're just writing it all out long form in a file, and it's certainly not possible if you're writing it all out on a whiteboard. So for me, this is a really useful tool to add to my tool belt, and one that I wanted to share with you guys. And so what I'm going to do is I'm going to try and figure out how to do exactly the same thing, but in some other languages, and then I will share some videos on that if people have found this one interesting. One final note I would say is, obviously there are other ways of practicing your algorithms. You can use services like HackerRank. There's lots and lots of different places where you can test and train for algorithms. But in my mind, finding a way to do this from the ground up is much, much better. For one, it's an education. For another, you're not relying on someone else's software and services to tell you how to do stuff. And at the end of it, you're more in control of what's going on. And I think that's a very important thing for developers, and something that developers don't realize is so attainable. Anyway, like I say, if you found this useful, just let me know, because I'll make more. And have a lovely day wherever you are, or night.